In this video, I'd like to talk about how we can modify the Carnot engine for power generation into something more practical. First, I have to discuss what is impractical about the Carnot, but what I'm going to do is I'm going to just briefly review the Carnot cycle and then talk about the Rankine cycle. Okay, so with what we described with the Carnot cycle is that I have a boiler, a turbine, a condenser. I never seem to leave enough room for my pump. And a pump. And the boiler boils a liquid, brings it to high pressure. A turbine relieves that pressure, extracting work. Or I suppose I should call that W of turbine. Then the condenser removes heat. So this is QH, this is QC. And we have to do work on the pump to bring it back to a liquid at high pressure. Okay, so that is the Carnot cycle as we've described it. But in order to discuss what is impractical about it, let me draw the process on two different phase diagrams. So I'm going to talk about the TS diagram. Here's the two-phase region. Here's the critical point. And state 1 is a saturated liquid. The boiler takes us to saturated vapor. The turbine operates at constant entropy. To produce something that is mostly vapor. And the condenser takes us to state 4, mostly liquid, and then we go back to state 1. So this is the pump. And the boiler allows for the input of QH. The turbine allows for the output of work. The pump is going to require work input, and it's going to be necessary to reject heat by QC. Let's also look at this from the point of view of a pressure enthalpy diagram. So the two-phase region tends to look like that. The critical point may be over here. Saturated liquid. I should actually label these. This is liquid, vapor, and this is liquid plus vapor. This is going to be liquid, vapor, liquid plus vapor. Going back to state 1, the boiler takes us to state 2. Now, the turbine doesn't work at constant enthalpy. It reduces the enthalpy along a constant entropy line, which I'm not really sketching here. Constant pressure in the condenser to state 4, and again, it's going to be the constant entropy line to get to the pump to get back to state 1. Okay, so again, boiler, turbine, condenser, pump. And let's talk about the issues. For one thing, if I have constant entropy for the turbine and I start as a saturated vapor, what's going to happen is that as I move down at constant S, the amount of liquid in my vapor is going to increase. So now we're back in the two-phase region. We may have had saturated vapor here, but this is a mixture of liquid and vapor. And again, I'm not a mechanical engineer, but I understand that turbines do not like to work with mixtures of liquid and vapor. They can be damaged by liquid droplets. So they really want to operate in the pure vapor phase. Likewise, you can have a pump operate with a mixture of liquid and vapor, but that's not advisable. I believe that may be damaging to the pump for the same reason as it's damaging to the turbine, but also pumps that are designed to work on vapors are far more expensive. So we would really like to operate in the liquid phase for our pumps. So here are the changes that we're going to make. What we're going to do is we're going to remain at constant pressure, but we are going to actually superheat to get to the new point 2. And in principle, if we had an isentropic turbine, we could still go straight down, and we would get, that is meant to be straight up, and let me redraw that. So isentropic, there. Okay, well now I'm not drawing, I think I need to redraw point 2 as well. So let's draw this and then go straight up and connect. That's our point 2 now. So we're going to go superheat. Notice that I'm going to drive the temperature up by a lot in order to touch or stay in the vapor range for our turbine. We can still output a saturated vapor and we can still condense, right? But now let's change state 4. Let's condense all the way to liquid. So this is my new state 4, so that when I operate my pump, I'm purely in the liquid. The new state 1 will move in this line. Maybe hard to see or hard to tell on this graph, but this is meant to be a constant pressure line because the boiler operates at constant pressure. Right? So when I have subcooled liquid and I start heating it, the temperature will rise, then it will be pinned, and then it'll rise. So I'm going to have large temperature gradients on my boiler. So this is no longer a reversible process, but it is more reasonable. It is more reasonable to have a boiler take a subcooled liquid, heat it up, boil it, and then superheat than it is to have a pump or a turbine work on the mixed phases. Now, let's see how we can change the diagram in the pressure enthalpy direction, right? So the boiler operates at constant pressure, so that's actually going to bring us here. So our new point 2, which I apparently never labeled before, this was point 2, is at the same pressure but a higher enthalpy. Maybe I went a little too far. Well, we'll adjust it. And I'm going to follow a constant S curve to bring me here. Maybe I'll move that a little. And I'm going to redraw this. There's my new point 2. My new point 3 was here, is also here, and I need to do more condensing. And again, I'm going to condense all the way to liquid to get my new point 4. My pump is going to add both pressure and enthalpy, which will take me up here. And I'll have a slightly subcooled liquid, which makes the boiler do more work. The last thing I want to add, well, hold on, let me just say that what we're sacrificing here is going to include efficiency, right? Because let's imagine my fuel now has to burn at least this hot, which is actually far higher than the boiling temperature of the liquid in the boiler, right? But it has to operate this hot in order to get the temperature this high. So we're going to have some pretty large temperature gradients, right? So maybe even this big, right? In the boiler. So that's clearly not a reversible process anymore. So the efficiency will technically be lower, but it'll be more practical to build it. We can also account for the fact that the turbine and pump may not be perfectly efficient, right? So if we have to account for entropy generation in the turbine, usually we go like this, and what we do is we look at the isentropic delta H, which would be the difference between this and this, and we say that the actual delta H, the actual output work, is going to be less than that, so it'll be something like this in terms of state 3. Likewise, the pump is going to also have some efficiency less than 1, so it's going to actually increase the entropy. So it'll move something like that, right, if we want to consider non-ideal pump. And the actual, I think, yeah, the actual H you get would look something like this. I'm not sure if it'll be on the left side or the right side of the isentropic curve. I'd have to actually look at a real diagram. But it does show you how you can adjust things for a real system. And again, this starts coming much closer to an actual power generation cycle that you would see in your power plant.